Hello.
Good morning.
Morning. How are things?
Turn this up a bit.
Hello.
Hi, how are you?
Great, great. How are you?
Okay. Haven't seen you in a while.
Yeah, I was actually busy. And last to last week, I had actually sent you and just, I think, a Google Doc.
Okay.
Uh, I could not get the time to join the meet last week. So, I had actually sent it I think, 4th of July. But the meeting was, I think, cancelled or postponed.
Oh, yeah, yeah. Okay, yeah. I'll have to re up that doc because I don't know. Well, maybe I did take a look at it, but I can't remember right now where it is. So,
Yeah, I mean, yeah, I can share if you want. Yeah. I mean, I can
okay.
present or share, whichever way you feel great.
Yeah, why don't you present it? Yeah. Well, you can do that maybe after we go over the meetings. Would that be good or?
Okay, okay.
Yeah. All right. And Jesse's here. Hello, Jesse.
Hello.
Hi, how are you?
Okay, it's been a very busy since we last spoke. Uh, just a lot, a lot has happened in a good way, mostly. Um, but it feels like we were just talking yesterday at the Friday meeting,
Yeah.
and
Well,
since then, I what's that?
yeah, we were. Yeah.
Yeah, and since then, I feel like I walked around most of the city of Boston, did some food things, a lot of conversations, nerdy conversations, and then went to an event at MIT. It was actually the MIT Rap Club with like an Ecolopto type salon, and it was like this cognition. It had a lecture from Michael Levin virtually, of course,
Oh,
but it was really interesting, really interesting. And I think I get a bit more of a sense of we talk about, well, what's this platonic spaces type thing. And so it kind of got into his platonic spaces idea a little bit more, which was nice. Also, I think I want to make sure I say his name right. I was just looking at it actually. Uh, Wasulu, Wasalu Jacko, otherwise more popularly known as Lupe Fiasco,
oh,
was one of the people there. And he's actually a professor at MIT, teaches at MIT for like rap theory
oh yeah.
and other things. And he was fantastic. Biggest surprise of the day, and I didn't expect him to be bad. But he was really, 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 really good. Like his ability to articulate concepts, um, and like trying like doing more curriculum and teaching and building, trying to bring people and understanding interdisciplinary spaces. I was blown away. Like he was remarkably the ability to deal with the different realities of like there was like a business side of things for part of what he was getting at, but also um like very phenomenologically aware, an ability to understand some parts of neuroscience, a way of speaking to the artist and the creative and the person developing ideas in ways that were really coherent. It's like great, just like great teaching. So that was like the highlight for me was that, just because I love seeing people teach interdisciplinary, multidisciplinary, undisciplinary things well. So I was really impressed by that. Um, but mostly I spent since we last spoke. Um, Talking a little bit about that and talking to some of the colleagues. I mentioned Molly before, who's doing things with Diginess and everything else, but folks from the Neuroergonomics Conference and just people visiting town in Boston for related events. So it was a very busy day, and today hopefully will be a bit quieter. I may have to step away at 11:30 for something else as well, but I'll be around in the meantime. There's other updates to
Okay.
say, but that was like literally that's been my existence has been all of those things, um, including trying to navigate against the grain when uh, like Fenway let out, and I was
Oh boy.
finishing dinner with people, and I was like, oh, like I'm trying to go the way that the opposite that they're leaving the stadium,
Right.
uh, and that was sort of the uphill struggle of the moment at that time. So just lots of like kind of fun, fun nerdy Boston type events. And then of course we had this meeting, and then I appreciate kind of the check-in from yesterday. That was kind of a little bit awkward on my part, and as in like thanks for making it work. I think you guys handled it well, and it's cool to hear the stories then. So yeah, if people missed the Friday meeting, there were some good things there too. But
Yeah.
it's my brief update.
Okay. Yeah. Thank you, Jesse. That was good. Yeah. That was a good update yesterday. Yeah. All right. So why don't we get into the different meetings for the week? So we had 3 meetings this week. We had DevoWorm on Monday. We had Cognition Futures on Wednesday, and then we had our open source meeting on Friday. And so I'll go through those. I won't go through the Cognition Futures meeting so much, but definitely the other two. All right, so this is the DevoWorm meeting from last Monday. It started out with Morgan and myself and Susan, and we had a little bit of a conversation. I started talking about Barshan's project here. So Barshan, of course, and I'll talk about this in the open source meeting where he presented on his progress so far in Google Summer of Code. But he issued a pull request to DevoGraph, and it was accepted. And I just went through this. So this is issue number 59. Implement dynamic tensor masking, loader and optimize EAM latency. And so this is just going over some technical additions and improvements to the graph attention method that he's working on. So that was kind of going over that repo. A lot of interesting things there. And then we had some more discussion. And then Ashu actually presented. She was working on some things in a Jupyter notebook. She's also working on graph attention, a little bit different approach to it. So she was presenting on her things. She took some data and did some analysis, and we discussed that a little bit. So congratulations to Ashu for that. Then we had some more conversation about the graph attention stuff. And then we did this paper here, which is something that Susan pulled up. It was a paper on using diffusion models to build like kind of an analysis of mechanical systems. And it mimics something called finite element analysis. So the title of this paper is AI-powered hybrid data-driven framework for finite deformation, which is probably not the best title they could have picked, but considering what it was about. But it was in the International Journal of Mechanical Sciences. And so Susan wanted me to go over this paper, and actually Ashu found it interesting because Ashu is interested in this area of PINs, or physics-inspired neural networks. And so they kind of talked a little bit about that in this paper as well. So it's really kind of an interesting paper, if not very dense, with respect to the methodology. And so just kind of going over the paper, they basically used a diffusion model to build this data set. So they had one of the problems in this field is that they can make observations in the lab, and it gives them a data set that is rather noisy. And even though it's controlled experimentally, it doesn't give a lot of instances of observations. And so it's hard to build continuum models of those physics. And so what they're doing here is they're using the diffusion method to build a new data set using this technique of data augmentation, or diffusion-based data augmentation. And that means that they're generating more data, cleaner data. It's actually a sparse data set, but it's covers more of the space of what you're interested in. And so then you can map it to some sort of continuum model of physics, and you can use a Lagrangian description and build a finite element model and look at different things that you want to look at. So that's what they're talking about here. And the idea is it improves performance of the models. And part of this, of course, is to have a model of physics-informed neural networks and to use that. They talk a little bit about pins as sort of the state of the art in the field. Already, not doing what they're doing in this paper, but they're looking at pins very specifically. More generally, pins and deep operator networks, or depot nets, are used, or at least people think they have significant potential for solving complex partial differential equations by integrating physical governing equations with model-free modeling, which is to say that you can have a model of some phenomena, you can create some governing equations, and you need to solve them, and these methods help you do that more effectively. That's basically the idea. And so they talk a little bit about artificial neural networks and their universal approximation property, which enables them to approximate any continuous function when their parameters are properly set. And then in pins, the governing equations are directly embedded as regularization terms within the loss function. And so you can both fit the laws and adhere to, or fit the data and adhere to physical laws. So they talk about this in the context of material science, where you have a number of problems, like recreating a stress strain curve, modeling plasticity of materials, modeling deformation of materials, and so forth. So a lot of nonlinear relationships in these data. And so then basically, we went over the math and some of the sort of the conceptual framework here. The math was pretty intense. So, but basically what they're doing is they are building a Lagrangian, and then they're building these stress strain pairs. So there's this graph that Susan talks about a lot called the stress strain curve, which is comparing stress with strain. And it's usually, for a lot of materials, it's nonlinear. And, she'll model that for embryos. And, an embryo being basically a soft active material, it has this highly nonlinear stress strain curve. And the idea is that you can recreate these stress strain curves using a diffusion process. You can model it as an idealized curve, and you can add noise to it with a forward process until you obliterate the curve, basically adding data points until it's totally random. And then from that, you make the solution more robust, so you can recover stress strain curves that are not, idealized. And so that's what they were doing in part of the paper. The other part is that they have these stress strain pairs that they model mathematically. And so that gives you some, it gives you detail about each part of the function. Okay, so that was a good paper, and we spent most of the meeting going through that, talked about the implications of it. They also did some things like KD tree decomposition and other things. They had this very long pipeline, from what I remember, where they actually had like 3 algorithms. They had a forward diffusion process and a reverse diffusion process. And, this is kind of going through what they were doing to create this data set and then testing it out and trying to solve the equations. So Shu had some things to say about it. Susan had some things to say about it. And that was our meeting. So it was a good meeting. So our cognition. So in DevaWorm, a lot of times, we'll go over a number of papers. Sometimes we'll do presentations. And in the last case for this week, we just kind of go deeply into one paper. So I like those weeks because it's a little more informal, but it's also more formal because you have to sort of pay more attention on what's going on in the paper. And I like to break down papers like that because sometimes they're very, they have a lot of unique properties we can untangle and link to our work. Okay, so then we had our Cognition Futures meeting on Wednesdays. I grabbed a recording of this. We did this paper, Is There an I in AI? And this was by Douglas Hofstadter, who is, we'll call him a classic AI researcher, or classical AI researcher, because he's been doing AI research for 40 years at least. And he's generated some pretty good students. People have gone on to be major names in the field. And then, he has also written books on like cognitive science and philosophy and mathematics, which are really interesting books. If you've ever heard of Gödel, Escher, Bach, or, there's some other books that he's written. And, he's covered a lot of different things. So he's not just a classical AI researcher, but a classical cognitive science researcher as well. In any case, there is this paper that he wrote in the special issue of Royal Society A, this issue that we were published in, and that is, we talked about a few weeks ago in depth. But we went through this article in depth in this meeting. So, it was a pretty interesting paper. He takes kind of a alternate view from like the sort of the mainstream view or the mainstream critique of modern AI, as well as a lot of the stuff that people were talking about sentience and all that, and just kind of like giving sort of his view or the grounded from sort of that mainstream point of view. It's interesting. And, he does it without sounding like a crank, basically. Because, you can have people who kind of work outside the mainstream, but they have kind of their pet ideas that aren't very well supported. But in this case, he's very much has a good perspective on this. So, here in a nutshell is the thesis of this essay. When words act like things in the world, they refer to those things, they mean those things. If and when that happens, the thinking is taking place behind the scenes of those words. And when there is thinking, there is consciousness and a genuine, fully fledged I. So it's about like kind of identity of an AI model. If like say, for example, we want to look at the potential for sentience in these models, then it has to have some sort of I, or it has to have some sort of identity, or, self-centeredness to it. And that's what he's getting at with this. And, it's very much a problem of classical linguistics, and it's a problem of kind of situatedness and all these things that, a lot of the AI research right now, quite frankly, doesn't really talk about too much. And we talked about this yesterday with the, the papers, the technical papers that we get from Anthropic or Meta. They don't really tackle these issues in too much depth. So, it's good to have this kind of perspective out there. But he's also talking about meaning in language models and large language models. So he talks about this a bit in his experience with using like a GPT model. And, there's this thing that we talked about in the meeting. I think it was Amanda who brought it up, where there's this list of things that you could do, or if you prompt a model, maybe say to you ask it to explain how to make a stable pile out of a book, a laptop computer, 9 eggs, a bottle and a nail, and then the model will give you an answer, and then that's kind of the thought experiment that he gives. And so, Amanda was kind of fascinated by that, and she was talking about, what the implications of that are. And we talked more about like kind of what it means to be kind of maybe sentient or to have an eye. And we got into this discussion about sort of degrees of awareness or degrees of, we'll use the term consciousness, but you could. The point is that you have these degrees of this thing that we're kind of wanting to identify in these models. And Avery brought up a point about how if people are drunk, sometimes drunk people kind of make like 80% sense or 60% sense, and you're sort of impaired, so you're not quite, at your full potential as an I or as an aware being, but you still can give a coherent answer. They were connecting that to this paper. So, and that's good. We had a lot of good discussion on things like that. Talking a little bit about Douglas Hofstadter, and I pulled up this idea of Hofstadter's butterfly because we talked about this notion of like how it connects to some of the things we've been talking about with Thomas Fuchs and resonance. So, resonance, of course, is a physical concept, but it's also sort of this analogy they use that's often used for awareness. And so I thought it was interesting that Hofstadter also proposed this, I guess it's a strange attractor called the Hofstadter's butterfly, where you get this pattern from a lot of these different types of, I don't know what his PhD was actually in. I don't think it was in cognitive science. It could have been mathematics or something. But it was interesting that, you develop something like that, and then you kind of work your way into cognitive science, and it's like, it's interesting stuff. A lot of connections being thrown around the meeting, and then, of course, he had some. The reason I said before he was non-mainstream is because he was kind of critiquing some of the mainstream schools of thought. Like he mentioned the Chomskyan mafia, or the Chomskyan crony network, or something. Whereas like all the people trained by Chomsky or had that Chomskyan approach to language, that they're kind of in their own kind of world, and they have their own ideas about large language models and whether they're aware or whether they're sentient. And then he talked about Searle and John Searle's work on the Chinese room, and this is kind of bringing these classic cognitive science concepts to bear on a lot of what we're doing today, and there's just not enough of that out there, quite frankly. And it's really good stuff. It is a bit written a bit like sort of axe grinding exercise, but that's just kind of maybe the way it needs to be written. I don't know. Anyways, Jesse creates these meeting logs where we post things from the paper and other notes in here. So I appreciate that Jesse does that, because I think it's useful to go back and look at that after the fact. And then our Friday meeting was open source. So Barshan started us off by giving a presentation of his work for several different weeks of Google Summer of Code. This is his midterm evaluation. I think it was last week. So, he broke this down week by week, kind of went through a lot of this stuff. and on to the next steps. What do we have? And kind of thinking about what needs to be done to finish the project. There's tool building and visualization. There's integrating the temporal data and scores, and then a final wrap up. And so a lot of documentation to build, a lot of different types of improvements to what's already been implemented, and then refining that pipeline. And of course, we need to kind of think about how to, I don't want to say advertise this, but how to make it, sort of put it out into the world. And of course, we need to kind of think about a paper for this as well. So Morgan had a lot of things to say yesterday about some of the things he's been doing, and he had some things to talk about agentive AI, and he had a lot of different links that we opened up and looked at. So we had this discussion and kind of went through this stuff, and then Jesse was visiting from Boston. And I gave a little tour where he was. I think it's the art museum there, and gave a few updates. And then let's see. Yeah, we went through. We had the discussion with Morgan first, and then we went through the links. So as it turns out, Barshan was accepted into this program, Claude for Open Source Science, or open source software, and it's a nice little program that is for people who do open source contributions and work in open source. So congratulations to Barshan for that. And I think it just gives you like access to some of the tools that Claude has, or that Anthropic has. And we talked about a few more things about that a little bit later, because then I presented on this article, Managing Complexity, the Primary Concern of Software Engineering. And this is from Russ Poldrack's book, Better Code, Better Science. And this is kind of a excerpt from that chapter. So it wasn't like a greatly in-depth article, but it did talk a little bit about modularity specifically in software project complexity, but also gave a definition of software design complexity, and so how we think about complexity. Now, this was just kind of I think probably a first pass approximation of complexity for software management, because it's like it's quite a deep topic, and you could have a lot of potential definitions for different aspects of software design. We talked about this late in the meeting. Well, one of the things you can do to minimize complexity is to make software modular, breaking your software down into different components and then linking them together selectively. And this was discussed in terms of a workflow, where you have these different stages of the workflow, and you do things there and then pass it off to the next stage of the workflow with minimal kind of interference. Okay, so, and then there was this book that I brought up, that was brought up in that article, called A Philosophy of Software Design by John Osterhout, and I went through the table of contents on that. And so, yeah, these are the links that Morgan pulled up. A lot of interesting things. This paper here, let's see. I can't remember the name of the paper. Oh, here it is. Verbalizable. It's basically about global workspaces and language models, and how they can design these. So it's not quite what we have been referring to as a world model, but basically it allows for us to have this type of model for agents. And so that's and then this is the repository. This is this notion of the Jacobian lens, which was in the mentioned in the paper. Though this is the name of the paper: Verbalizable Representations Form a Global Workspace and Language Models. And so it uses this Jacobian lens, and it's basically applying a Jacobian over a text corpus to pull out different aspects of the language or of the language in the corpus, and then using that for the language model. Yeah, so that was our meeting there. Okay, those were our meetings for the week. I see that someone wants to say something. I think maybe Morgan.
Um, well, I'm actually just getting on the bus, so let me
Okay.
hold off.
All right.
But yeah, I could say a little bit.
All right. Yeah. Jesse or Kavya, you have comments?
Um, there's a lot, as I think said at the museum yesterday. There's a lot that I'm taking a lot more. I'm taking quite a bit from the philosophical transaction issues in a nice way, because as much as it's sort of world model centered, what I really see the issue as is sort of a lot of people whose ideas I largely care about in a way that are touching upon AI, but not necessarily beholden to some aspects of AI that are popular right now. Like we have the Gershman essay on the hard problem. It kind of humorously titled, or it wasn't titled that, but it was the hard problem versus the easy problem, and what he was talking about. Like that was very, and that's something that I'm continuously wanting to reference. The Hofstadter piece is interesting, even in the context that, I mean, Bradley just went through it, but even in the context of the history of people talking about those things. I'm still thinking about the topological piece, where, what the topology, which actually I was going to try to mention yesterday in some of the Levin related talk about what's going on. Our piece is there. We're looking at another piece next week, so I think I'm kind of, a lot of what we've been covering in the Cognition Futures Reading Group in the past has kind of been almost like going in depth on a particular line, and this is more of a breadth of perspectives, kind of essentially around a topic. Like it's about world models, but also about like LMs. It's also about kind of sort of the current state of cognition and AI and how they're relating to each other. So um, it's it's interesting in ways that I didn't expect. Um, so I'll just say that there's a lot of, my mind is flowing with a bunch of things that came up in the last few days, um, about sort of those topics, and one of the questions that I guess where I'm going with that in some form is, I'm really curious what we're going to want sort of projectize, uh, because I know, Amanda's kind of along for the ride of, oh, let's do fun stuff, and we're not really pushing anything right now. I have things that I am interested in doing, um, but there's a lot of um, there's a lot of how do I say it? There's some. I just got a bunch of messages from other stuff in my face right now. Um, I feel like hmm, I'm sort of in this, not quite dilemma, but I'm in this moment of, one. The main focus right now for summer is a little bit elsewhere with data and direction and all, and the Google Summer Code and the joint open source stuff, whatever. Yes, but I I feel like there's some very interesting things, and it's just going to be how to build that out, and also how to build that out with some of the relative. I'm forming some broader projects that I'm wanting to put forward, and it's sort of like, in what light is the best light to present them relative to all the things that are going on in it's so funny to phrase it this way, but all the things that are happening in the broader community here, like the lab proper, and then even the by extension some of the Ecolopta stuff that I mentioned, and the 11-ish talk that we mentioned before. Like I saw this, I didn't get to look at it entirely, but there's a preprint by a paper by Benjamin Lyons, who we talked about a little bit before with the sort of economic lens and his whole thing about price setting and economics as these sort of systemic ways to relate to um, you know cognition, like basically applying economic lenses to cognition and sort of work with Levin on that front. Like there's just a lot of things that are sort of like, oh, it could go this way and this way, this way and this way. So excited about that, but I think that will I think to have a little macro admin hat, I think that's going to sort of potentially be a as August blooms, I think fall may be a fall of particularly interesting focus of some of the things we're talking about here, like what I'm basically alluding to, and then also I'm hoping the Future Center at JoPro will be a bit more. It will be coming online, and there's stuff happening now there, but my little segue here also is both. I'm open to sort of any discussion now about like what we want to do with what we're doing in the reading group, or like this other more so the various strands of thoughts that are coming up in it, and also potentially any more thought about like year end, so I should say summer end events and dates that might be interesting to hold some kind of an event at if people have any of those. So that's my contribution.
Okay. Yeah. Oh yeah, we did talk about the Google Summer Code Reunion. That's probably on the horizon. But yeah, we do have different things that we'd like to maybe do in the fall. We'll probably do something for the Active Inference Symposium. I actually am thinking of trying to do an event on the special issue, because it turns out a lot of the authors from that special issue will also be at um, the symposium, and hopefully we can maybe touch base on some of that there.
Yeah, that'd be
It's gonna
great.
work out, but yeah,
Is that usually in like October, November or something? Okay.
November, yeah. But it's kind of one of these things where um, we have, like, I don't know if maybe they'll be presenting on the papers already, but maybe to have like a discussion group. I have to work out the details, but I think it'd be nice to have like some reflection on that after the fact. So it'd be nice.
Yeah, and I'm certainly interested in helping out with that if that's um, when that happens.
Yeah. Um, so that's good. Yeah. Thank you, Jesse. Well, welcome, Vidhi. How are you?
My mic keeps getting connected to my phone. I don't know why. But hi. Hello. Yeah.
Yeah, I can hear you.
Audible? Yeah.
Yeah.
So I'm good. I have my last day of internship on Monday, and I was actually thinking if I can join from the laptop and show all my project or whatever I did in the past 2 months. But also I'm scared of their rules and policies, so I'm thinking I'll see if I can join from that laptop because I have nothing on this computer or this laptop right now with me. But I really wanted to show you all. And I can give you a brief description of what I have done if we have time.
Yeah. What? Well, okay. We have Kavya wants to present, and then maybe you can present.
Okay.
Maybe we can share your laptop by then, and we can do the.
Yeah,
Yeah,
sure.
that'd be good.
Yeah.
Okay.
Yeah.
All right. Yeah. Thanks. I'm looking forward to that.
Yeah.
Good to see you again.
Yeah, I'm busy. Okay, I'll figure out that thing till then, and then I'll join from there. And if I can't join from there, I'll let you know.
Okay, sounds good. Thank you.
Yeah.
So it looks, I don't know, Morgan, are you situated? Would you like to?
I'm still on the bus, and there's still a lot of potential drama that would come up if it's okay to give me maybe like
Yeah.
5-10 minutes, and
Okay.
yeah,
Yeah,
happy
that'd be good.
to contribute. Yeah.
Okay, yeah. All right, Kavya, why don't you go ahead and present?
Okay. So basically, these were some of the questions in my mind while writing about these papers or the discussions on it. So uh, the question was, when does the developmental transition actually happen? And is the timing fixed like a clock, or is it encoded in the genes? Like after a certain amount of steps, this should happen, or um, I mean, is there a following order? Like first this should happen, then the next, and what actually drives this development forward? So the first theory I came across was uh, Gassell's theory. So these were some of the points which I mean, liked about it. Like children follow the same developmental sequence, even though their individual pacing is determined by genetics. And also there is reciprocal interviewing, like two opposite tendencies eventually come together to create a balanced one. Like even if you have two, like in the initial stage you work more with your left hand than through your right hand, then eventually they get to a balanced stage. And third point was the developmental progress was in a spiral pattern. Like there were some cycles of equilibrium, and also there were imbalance phases. So there's also a self-regulation concept. Like if something is getting too far in the wrong direction, the equilibrium brings it into the normal stage. So I this theory is actually, I mean, very famous among psychologists, but there have also been some criticism based on how it incorporates social factors into it. So I mean, this part was more mainly I was researching upon this because for my active inference agents, I wanted to know, like how should the development actually take place? Like, should I incorporate the biological trends or the uh, cognitive trends or something else? So this was the second paper, which was Gilbert's theory of probabilistic epigenesis. So here they have described development as some sort of helix where every time an organism interacts with its environment, it does not just reset to its previous baseline. The interaction permanently changes the organism at different levels, like behavioral, neural, or even genetic level, and it eventually moves forward and changes the boundary of the system. So yeah, this was some uh, good thing, or the some interesting thing I found in that paper, like indeterministic determinism. So the boundary, the agent, so organism current state and the environment strictly define the outer boundaries of the causal tube. So here the causal tube is basically the interconnection between different layers, like the genetic layer, neural layer, behavioral level, and the environmental level, and they are interconnected through time. So you are limited by what is biologically and contextually possible at that exact moment. So this is what defines the boundary. And there is the freedom part. Like within this tube, the field is actually internally open. So the exact specific form or behavior that will emerge out is not preset. So the organism can grow within this tube within the constraints, and the phenomena which will occur will be novel. So year two, the development is said to be a continuous process that is constantly in motion. Um, the third was dynamical systems theory. So this is again sort of a continuous process theory, but they have used self-organization as the main concept here. So development occurs when multiple independent parts of the system, like the baby's muscles, nervous system, motivation, physical environment, come together to solve a specific problem. Behaviors are generally softly assembled on the fly rather than being hardwired. So when a pattern like crawling or reaching works well, it becomes a stable habit or attractor. So although the development is continuous, there are some attractor states where they become stable. So because there is no internal blueprint telling the child what to do, development relies heavily on random, spontaneous exploration. So development here is not always slow, steady incline, and often features sudden leaps or phase shifts, like suddenly knowing how to walk or suddenly passing a cognitive test. So more of like chaoticness and some stable states as well. So these hidden shifts happen when a control parameter reaches a critical threshold. The control parameter was a single variable, such as gaining a bit more muscle strength, a change in leg weight, or gaining specific new experiences that disrupt the child's old habits. So when the old habit became unstable, the whole system reorganizes into a new, more complex and more mature behavior. And this paper had also compared various other theories like Chomsky, Gibson, Vygotsky, Piaget, Smith, and so yeah, this was more of how they were comparing their dynamical systems theory with other theories, and this is again more a bit in depth of these about differences between the theories. So based on the mechanism of change, Chomsky relies on maturation via triggering and parameter setting. Triggering releases pre-existing options via environmental cues, while parameter setting uses environmental signals to select matching options from an innate grammatical array. So basically, as I mean, even here, between different theories, there is an different importance given to what effect the environment has on the developmental growth. Then Gibson's main mechanism was perceptual learning, like through exploration. Children discover matches between their own physical abilities and the affordances for action available in a structured environment. Whereas Vygotsky was more on social internalization. Cognitive and linguistic structures are initially experienced during social interactions with competent adults and are subsequently internalized by the child. So this is more on the interaction between other competent adults and the child and what it learns from the competent ones. Piaget main mechanism was constructivism, which was driven through bidirectional processes. Like children act on the world and adjust their mental structures based on their success or failure. Whereas this dynamical systems theory was driven by self-organization, as mentioned earlier, where pattern and order spontaneously emerge from real-time interactions between internal and external components without any pre-existing instructions. The Ellman and Bates theory. Again, the mechanism here is emergent learned connections, where change occurs by shifting weights among a subsymbolic neuron like nodes to track statistical regularities in the environment. And this is again the second layer of classification among theories, where the role of external information and experience. So nativism downplays the environment, like claiming it is too sparse to provide real structure, acting merely as a minor batch trigger. So yeah, it does not take into account much of the environmental effects, whereas perceptual learning views environment as already highly rich and structured. The child doesn't need to invent mental structures because the information is already full and available to be discovered. Constructivism asserts that external information triggers a state of mismatch that forces the child to adapt, but the final cognitive endpoint is not explicitly found within the environment. Connectionism and dynamic systems. theory both give heavy structural weight to the environment. Connectionism directly incorporates statistical patterns into its system weights, and dynamical system notes that while environmental shifts after developmental outcomes, the precise final form is an emergent property of the whole historical system, not something pre-packaged in the environment. So basically, these two theories give more importance to the external environment and their behavior on the development. So this is another, you can say, a class of classification type, like on what basis they are classified. So it was social interaction, biological constraints. So out of all the six theories, Vygotsky is the only framework that deeply integrates social interaction as a primary engine of cognitive structure. And nativism explicitly denies its structural relevance, while Gibson and Piaget acknowledged or bypassed it without active study. The authors admit that dynamic systems has historically failed to adequately integrate social factors into its research. And biological and brain constraints, except for Vygotsky, all modern theories accept biological constraints. However, dynamic systems and connectionisms are uniquely constrained by modern developmental neurobiology, such as brain plasticity and activity dependent neural growth, which contradicts rigid nativist biological determinism. Fourth was sensory motor foundations and embodiment, like the embodied mind. Piaget, Gibson, and dynamic systems heavily prioritize the body's physical structure as the baseline for higher reasoning. Like you need to have a body to be considered intelligent or for growth and development. Whereas Chomsky rejects this, viewing grammar as an entirely autonomous mental faculty detached from the physical body. And the connectionist models also rarely feature sensory motor interaction or physical embodiment. Mental representation. So basically, Chomsky, Vygotsky, and Piaget assume traditional physical symbol systems consisting of stored timeless internal rules and propositions. So basically, they are defining everything based on some uh, formulas or rules that are constant, whereas Gibson rejects internal representations, and connectionism and dynamic systems view representation as temporary, recurrent states or activation of stable habits that occur close to the body's sensory surface rather than hard coded physical symbols. So basically, uh, in traditional representation, you have symbols and rules so that you can match these states again and again. Whereas in Gibson connectionism and dynamic states, they have told that merely since everything is temporary, there are no hard coded rules. Sixth one is the dynamics, math, and simulation. So, connectionism and dynamic systems share a mathematical framework grounded in nonlinear dynamical systems. They model change across continuous timescales, showing high sensitivity to initial conditions and sudden structural transitions, such as catastrophes or physical shifts. Both framework utilize formal mathematical models and computer simulations to strictly test their hypotheses, separating themselves from the purely verbal descriptions that characterize historical child psychology. So basically, after reading some of these, I I feel that some theories say that development is a continuous process, versus some say that there are discrete stages or sharp stage transitions. So most of the above theories, I felt that they were contradicting a bit, because some stated that development is actually a continuous state, whereas some stated that there are actually spurts or discrete transitions that happen. These were actually some of the biological papers that I went through, although I did not fully understand these biological papers. So I just wrote down what I understood from it. Like, based on this paper, these are actually NCBI papers, all these three. So yeah. So first was that genes do not encode a master time clock for development, but provide the necessary tools. Like I initially thought that genes actually contain the time clock, but after this paper states that uh, the genes actually provide the tools for it, and there is dynamic feedback loop between the organism's current biological state and the environmental signals it is actively receiving that pushes the brain to continuously adapt and reorganize and develop. Uh, the second paper was how cells control developmental timetables. Like it focuses more on how different species run the exact same genetic programs at different speeds, like different developmental windows and different developmental timings. The genes provide the blueprint and the order of operations, but the cellular environment acts as the project manager, deciding exactly how long a cell waits at a certain stage before moving to the next. As I mentioned earlier, I could not understand much of the this paper because it had some biology involved. Uh, this was again a third paper, more again on the biological clock of the cells. So there were two kinds of timers that were discussed here, like the uh, count down timer and a count up timer. Like countdown timers have a developmental states that remains stable as long as certain maternal protein is present, and as the timer um, counts down as this protein steadily degrades. Similarly, there are accumulator timers which work in the opposite way, where they act when there is a certain amount of accumulation present. So yeah, most papers did not actually talk about how is the timing of transition happening from one stage to the next. Like is it decided or is it encoded? Like is it fixed? Like that after a certain amount of years, development should happen, or how is it? Like is it exogenous, endogenous, or like is it fixed? So none of the papers explicitly mentioned any of these things. So that was uh, a bit where I was stuck for some time. And more on the simulation part, I was thinking, like, should we keep it a timer based transition in our simulation? Because uh, I mean, it's not plausible to actually simulate the real biological development, and I could not actually find papers that explicitly mention how is the actual developmental timing. And or yeah, another decision was like, should we keep something where the learning plateaus but the external model requires more? Like the agent has learned only two of the hidden variables, but the model requires more hidden states, and then when the agent unlocks a new set of actions, it can infer the new states, and this unlocking phase can be called as a transition. Like from jumping from one transition to the next, it unlocks new abilities, uh, or there is you can say a new slot that can be filled. And this was the part I wrote recently. Like I took some decisions, like based on about thing I came across another theory which was catastrophe theory. So yeah, in that they have mentioned that whenever two continuous variables interact, there can be a cusp formation or a sudden jump that can be shown through a cusp. So I think that is where we can hold the simulation. Like I can keep a continuous learning environment, but based on the endogenous response, the agent can take a certain amount of action, and then it jumps or transitions into the next developmental phase. So basically, we can compare it to the catastrophe theory and say that something of it can emerge out of it. And yeah, I think current biological development is not plausible. Rather, development should be based on learning or similar parameters, as that what helps make the agents intelligent. And currently, I have decided that we can keep a continuous learning part and then transition this based on the learning plateau. Like I mentioned earlier, like we can let the catastrophe theory emerge if possible. But yeah, this was these were some of the points like I've been stuck on from quite some time. Like I've been pondering upon it, like what should I do about this. So first question was like, should the developmental trigger be just based on the learning plateau? Like if the agent has based on its current limitation or current model, has it has its learning plateaued? Like has it learned everything? So there is nothing more to learn from its current limitation, So in order to learn more, I need to put in more slots or infer more hidden variables from the environment. So I can unlock the new ability and infer the hidden variables out of that. And another um, side of it was like, should I increase, like, should the developmental trigger be based on the KL divergence? Like, if error increases, then we should expand. Like, the current model is not able to infer the current states, and it's giving a lot of error. So it's time for me to develop. So should I do that, like incorporating Bayesian model reduction or adding new slots? And uh, third question was like, what capability should the new developmental stage add? Like, should I uh, in should it infer new abilities? What new abilities should I actually add or give to the agent? So this was the part like where I've been stuck for some time. I think I went across some papers that talk about it, but I haven't made a formal doc or gone more depth into it. Yeah.
Well, this is great. This is a pretty detailed overview of. So what is the? I guess this is interesting. Some of these questions. So what is the kind of the action item here? What is the sketch of what you think the model should look like? And maybe
Yeah.
that's a
So
better way to kind of get around the being stuck part. Like, if you drew out kind of the components, like
uh,
this is what,
yeah,
right?
I mean, since the main part was actually thinking about the developmental part, I thought, let me first decide how the development should occur, and then I can work on the implementing part stuff and deciding what environment or what thing the agent should look like and follows. So decoding that developmental part is a bit uh, tricky, I would say, or where I'm stuck. Like, I'm thinking that the agent should in itself, uh, I mean, the learning of the agent should plateau, and that's when the agent understands that I have learned all I could from my current stage, and I cannot learn more or learn more hidden variables that the environment has to offer. And I need to develop in order to infer those hidden variables which I cannot right now. So, like, I'm able to infer current states properly, but I'm not able to infer some other hidden states unless I develop. So that is what I was thinking. But again, I cannot keep learning plateau as it is. Like, if I cannot, I mean, we do not know whether the agent has fully learned its hidden variables, or is it at a developmental stage? Like, is it fully matured, learned everything from its world model, or I mean, the whole model, generator model, or is it just that it just needs to do a developmental transition? So, I think I'll need to add something more rather than just a learning plateau. And also, I mean, there were things, or I think deep learning papers or ML papers where they add new slots or new neurons or new edges if the error continues to increase. So this is somewhat related to ML or DL side of things.
Yeah, I would try to, draw out like a map of all of this and say these are the parts that are kind of involved in this. And from that diagram, you can kind of parse out the pieces that you can actually model. So, what I mean is like, I diagram everything out that you show in this outline, which is great. And we might use this as like a review paper or something. Um, you can then kind of figure out the landscape of what needs to be done, and then you start kind of drawing boxes around the different pieces that you could. Okay, let me create a simulation for this. Let's see if I can try to do that. So, like modeling plateaus or modeling like environment or stuff like that. It's a hard, it's hard to kind of approach everything at once, right? Like
Yeah.
and because it's the kind of problem where it's also the kind of problem where you have this continual feedback. So it's more than like traditional continual learning. It's kind of like you need to have like an agent, and it needs to be in an environment, but it needs to kind of feed back from that environment to actually get to some of these other things. And so whether that just kind of emerges from your simulation if you create the agent that allows it to do that, or whether you uh, maybe need to add different components to it, um, then that's kind of how you know how that's going to look. So I'd start kind of small. I'd start thinking about, okay, what's the most plausible thing I can simulate, and then let's work on that a little bit. Let's get a working simulation, and then if I have to add parts to it, I can add in parts. And if I just think I can maybe represent it as a dynamical system, or represent it kind of as this highly controlled task, then you can kind of think about it in different ways and maybe implement the model according to different rules, according to different kinds of environments, and see how that goes. A lot of times, you want to kind of do experiments in the sort of the classical experimental design approach, where you say, okay, this is an experiment where I have different conditions. I'm going to set up my agent in different ways, and I'm going to run them and see which one does best, or maybe which one is maybe not a lot of them will do what you want them to do, but some will. And so you just say, okay, this configuration works. Let's move to the next step. Or you could do once you get a little farther along, you could actually use do different tasks where you ask the agent to do something, maybe like some sort of developmental learning task, and then see if it can do that. We've done stuff with we've done a lot of things in the group, various types of approaches where we've had these growing networks or agents that sort of gain an internal model over developmental time. We've also done things with, sort of a developing morphology and things like that. So we have some work on that, but we haven't done a lot with really investigating things like.
Is it available on the GitHub OREL? I mean OREL repos.
Yeah, so we have things. Well, we have different things in different states of repository. We really need to work on that a little bit more. But those things are there. Some of the code is, pretty straightforward, and you can just adapt it. Some of it's more conceptual in nature, and that's maybe what you would want to take forward from that. But I mean, it's fine to develop your own method. I would maybe focus on developmental learning, one thing. But of course, you talked about Gibson. We're interested in sort of ecological perspective, and I think that's actually quite useful. And some of the sort of debates between innateness and learned behaviors. So what behaviors can be learned, but what does an agent need to start off with as an innate set of features that allow it to sort of learn in the first place? And those are the kinds of things we've been working on in the group, at least from what you're doing. So we might be able to come to some, we might be able to really kind of hook that into what we're doing.
Actually, I even went through the canalization theory, like the innateness or canalization part of it. But
Yeah.
but the theory, I mean, there were some critical things which I thought that we cannot actually use that in a simulation, because I think the theory critics or states that we cannot actually determine the innateness of every environmental variable. Uh, I think there was one example related to rats population or something like that.
Yeah. I mean, there is this idea of a canalization function that people have worked out, like in the evolutionary programming literature. But again, it's like it's like sort of inspired by those ideas. So a lot of what you would be doing when you create a model is you're just largely going to be inspired by a lot of the theory, and because you can't model everything in the theory. A lot of theory is incomplete, by the way, so that's another problem. But you'll find it is a useful heuristic. I think that's it's definitely it's useful. But yeah, so I mean, I think this is great progress. Like I said, I think this outline is gonna we could turn this into a nice review. Um, and I don't know like what we'd have to rewrite it a bit to fit it into like a publication or something, or just as even a white paper in the group, where we kind of lay out what is developmental. People people talk about developmental AI all the time, and they kind of publish one-off papers, but there isn't a good paper that I know of that kind of lays down the gauntlet on what needs to be done. I mean, there have been a couple papers where people have kind of introduced the idea, for different audiences. But I think this could really become a paper where you lay down a lot of the framework for, okay, this is what needs to be done, and this is how we might do it. So yeah, this is a great outline, great start to this. But then
Yes,
working on these, working on
the
these
same
simulations.
difficulty I faced while researching about papers. Like, uh, there isn't an outline. Like, how do you actually create an AI that itself develops? There have been papers about morphologies or morphogenesis where structures come together to create a structure, like cells coming together to form a structure. Like mostly of Levin and Michael Levin's paper and other morphogenesis or related papers.
Yeah. Well, yeah, that's something I could help you guide you through because we've talked about that a lot, a lot of that stuff. So that's something we could do. I mean, it's um, yeah, yeah, we'll discuss that.
Yeah,
But
sure,
yeah,
sure.
this is great. Yeah, this is great. Thank you.
Uh,
Yeah,
yeah,
Jesse
thanks for
wants to
the
talk about it more
advice.
too. Oh, no
Yeah,
problem.
sorry,
Yeah,
sorry.
yeah.
Sorry, I could not hear you. Yeah. Did you say something?
Oh, I don't know. Jesse put something in the chat. Did you want to say something, Jesse, or?
Oh, just I mean, I was just following up saying, yeah, like this is I had to step away and I have to go in a little bit overall soon, but um I think developmental stages and a lot of what you're getting at here are something that there's a little history here, and I think there's a lot that can be pushed forward with this material. So let's even like it might be to the point where we it doesn't have to be during one of these meetings per se, but scheduling a time to really sit down and think, okay, where do we want to go with this in terms of papers or developing the project might be good to do soon.
Yeah.
Thanks for the advice. I'll try to model it somewhere and try some simulations and do something if that's possible. But I think it will take some time. Like, I do not know a lot of stuff on how to simulate an active inference agent, so I'll have to uh, check more on the coding part of it.
Okay.
Thank you so
All
much.
right. Thank you. All right. VD's been trying to log on here and set up. I don't know if you're ready to.
I do have the PPT on my personal laptop, like just the PPT. I wanted to show you all the other things also, like the code and whatever I use, but I don't think that's possible. But if we have time today or next time, then I can go ahead and show my PPT and just briefly talk about the work that I did. So, the name of the project is Alternate Data Insights. So, basically, I'll just give you all a brief overview of everything. Then, the future aspects of this can be that now that the pipeline is ready, we can just keep processing all the calls because earlier the pipeline was also not completely ready. So, we were doing everything of this project in parts. Then we can add some more features to it, and to optimize the cost we can build an in-house agent or something. Yeah,
That's
that
pretty
was
good.
really fun.
Congratulations, Vidhi.
Yeah,
That was a great
thank you.
session. Yeah,
Yeah.
so looks like you've got a lot of exposure to different types of programming and data science and
Yeah,
large language model stuff. So yeah, that's
right.
great.
Yeah,
Yeah, so that's great.
okay.
Thank you for sharing that.
Yeah. Yeah, I hope you all enjoyed and you all weren't bored or anything.
Yeah.
Yeah.
Okay. Morgan, looks like you're ready to give your talk. Go ahead, Morgan.
Yeah, can you hear me, Bradley?
Yeah.
Okay. I'm trying to fix the Linux Bluetooth with a non Apple Bluetooth. Okay.
Okay.
So, well, just wanted to talk about a few things this week that I didn't mention Friday, although I'll cover some of those too. 1 second. Let me see if I've got the right. Okay. So this is this is happening this week, the Neuro Academy. And so it's this neuroimaging data science workshop. And one of the reasons I bring it up is that you've got people like Russ Poldrack presenting there. So that you'd covered covered a bit of his book, and just to let people know that there's that all the videos are available on YouTube, and they've got a couple that are very so like managing Python projects with Pixie, using GitHub ecosystems to your advantage. Some things that are not necessarily neuroimaging specific, right? That might be useful. And so it's got a great lineup of neuroimaging researchers talking about their particular projects as well, with a focus on open source projects. So one of the videos came up last night, and I thought I should give him a shout. Also yesterday, after our meeting Friday morning, is there was a special or an event of Machine Learning Tokyo, and this is a group that's been around for a long time. Again, rooted in open education, open source, open science. And these are some of the events that Susanna runs, which, as you can imagine, have definitely taken a bit of the LLM direction. And it's funny because it's like I can remember far enough back in the deep history of deep learning where it was much more like OpenCV focused, or kind of like ImageNet focused anyway. But the field moves on. So evals was the focus, and Hummel, is was I think he's got some some projects too, but he was very nonsense about the evaluations, and the kind of evaluation work that he's covering is still very similar to what I was talking about, or the focus of the anthropic paper, as well as the Blaise Agarasiarchus kind of work, right? So how do you even, well, there's a lot of interesting overlap between kind of evaluations work as well as kind of like the AI safety work, in terms of really trying to understand what your model is doing, and how your model is aligned, right? Anyway, this is a good group. I'm just happy because because of the time zone. Usually her events are at 5 a.m. So it was nice to have one at 10 a.m. my time. Just to keep on the topic of because I brought up Emily Bender on Friday, and just to say that Dare, which is I forget what she's definitely a part of Dare. She was on the stochastic parrot paper, but it was interesting because she was kind of pulled into it, and because they wanted a linguist, but now it's of course its own. This is their certainly this is Dare Academy. I wonder, is Dare? Sorry, let me just see if Dare, what they call those. Okay, it still seems very education focused. But I wanted to just, shout out to Elvis here, because the Elvis is the one who seems to be behind a lot of the paper recommendations that are coming out from Dare. And so I posted in the Slack the metacognition and LLMs survey, but I just wanted to bring up this other one that Elvis just suggested, which is self-improvements in modern agentic systems, a survey with of course the esteemed but not esteemed enough, or something, not lauded enough, Jürgen Schmidhuber. So this is going to be good. But it was interesting to see, this is like definitely, if you're familiar with agentic coding, this is like the most agentic coded artifact you can imagine. But I'm still really interested to go through this in terms of this is the Schmidhuber Swiss AI team doing something on self-improvement, and they've got the awesome self-improvement agents list on their GitHub. So that should be good. The other thing that I thought Elvis recommended recently, and I'm not seeing it right now, but it's something like it's basically talking about harnesses, and the reason to the reason to talk about that, sorry, is the ARC AGI challenge, right? So there's I'll look it up in just a second, but someone's showing Impossible Labs, I think, is showing this, where they've got a something like a 93. Here this is, so the incredible performance on ARC, and it seems to be a lot of the particular harness that they're using. So I think it comes back to this question of what should we be, or how much of the reasoning and things like that, especially on long tasks like coding, are driven by the harness, as opposed to the base model. Anyway, since I do want to get to some of the educational materials that would be useful for learning about this, and I do have my Mike X Cone book today, so I can start to see how much is going to be useful here. But just wanted to shout out again to the Jeremy Howard work on this. Who seems to have himself as generating the first LLM. Anyway, that's the I think that's the updates I didn't cover that on Friday, but there are a couple of things that again, check out the Societies of Thought project on my GitHub, that is trying to take some of that Anthropic work, in addition to other papers, and like I put on the the Slack, there's this kind of connection with the University of Chicago. What is it called? The Knowledge, call themselves the K-Lab, Knowledge Lab. I also like dropped a link in the Cognition Futures. Sure. I was just looking at some of the speakers at this more EEG methods meeting that's going to be in September. Excuse me. And one of the speakers reminded me of her work together with Iris Van Rouge. How do you
like that.
Is that something like that? Yeah. Anyway, I dropped that reading women in cognitive science list. That was awesome. Not just for the kind of more contemporary speakers or scientists, but also for some of the historical readings going back to the 1600s that I thought were really very cool. Sorry, I can just really quick. And so some of these, Olivia Guest was the person who made me go down this particular rabbit hole, but I'm super interested to catch these before 1900 readings.
Yeah.
Anyway.
Looks pretty good. Yeah, thanks for sharing that. A lot of interesting stuff going on there.
Yeah. So be really, well, it's going to be, it'll be interesting to read the Schmidt-Huber on this. Apparently their lab thought this was interesting enough, but like we've talked about the ARC challenge before, right? This is no no small achievement, right? And it's not the first version of this, and it is, a lot of great people's best efforts. That's making real challenges for machines, and I think it's worth talking about again in terms of not only some of the more the societies of thought, like just in terms of like how nuts and bolts, how are reasoning models different, but and then like what the interaction is with the harnesses in that, but then something like this where it's you're doing program synthesis is how it's being described, and latent world representation is a program, not a vector. I think there's going to be, again, I think ARC is one of those challenges that pushes groups to really not chase to really try new things. And think it'd be worth staying familiar with that. Again, I still want to know how to link that back to computational cognitive science, right? Like of humans and animals and cells, but anyway.
The program synthesis, I think, is like kind of a more classic topic in, well, I mean, maybe cognitive science, but I know that there are like connections between them. When harnesses, when you say harnesses, what is that? Is this kind of a new term, or people have been using it?
People using it for So some of this comes from I'm not exactly sure. There's this Australian guy who kind of is somewhat credited with early versions of this. Again, I think it's one of these like Schmiber, Jeremy Howard things where a lot of people will say like, well, I was doing harnesses in the 1990s, but so one, it's like when people talk about a base model, right? Like, or they talk about an LLM being a transformer, right? The model that's trained to do the next token prediction, right? That's the base model. And then there's still a lot of work to be done in terms of now making that model. extended in time. And the harness is not only it's also adding features and tools and I think what you saw with the release of the code release of Claude Code. So again, it would be good to read the Gary Marcus the Gary Marcus piece on Claude Code release. Claude Code leak. Just because he's just like, this looks a lot like neurosymbolic AI.
Yeah.
but also being a loop. And so like again, like yeah exactly. But I think they bring in a lot of different functionality. And so then it kind of comes down to, what are you actually interested in it solving, like interested in it doing, right? And anyway, I'll see if I can find the first guy, but agent harnesses. Kavya is like, agent harnesses are like the orchestrating parts on top of LLMs to get work done in a certain way. It's but I think you'll see, that so Elvis has something on harnesses too. I'm trying to find the paper as soon as I do. But I think that would be let's see a survey of harnesses. And but I think it was some of the people on the ARC AGI topic that are talking about how it's absolutely worthwhile to be writing your own harness, partly for education, and partly for that's where you actually add value, when you have a particular task, like anyway. If you just put in Australian loop harness, you get a lot of non-LLM related references.
Australian loop. Yeah, got it.
Australian loop harness.
Oh.
But yeah, good stuff.
Yeah, so that's good. So yeah, so let me see. Kavya actually put something in the chat here about harnesses. I think agent harnesses are like the orchestrating parts on top of large language models to get the work done in a certain way. So yeah, it's reminiscent of the reasoning models as well, where you have these things that are sort of on top of the large language model output, and then that helps you refine the content that you actually use from the model. And I guess like a harness would be like supporting materials. I'm trying to think of how you might write a harness, say, for some application. So it's like a neurosymbolic maybe piece that you put on top instead of just having like the standard LLM. Yeah. So that would be something that would be built on top of it, or after the output, or inside the architecture. How would you go about doing that?
This is this is what. So we had the Ralph loop developer actually come and speak at the tower, and so unfortunately, his term Ralph Loop is now so ubiquitous that I can't find the actual guy anymore. It's just people talking about Ralph Loops.
Yeah.
But some of that was what he was trying to get at, which is it talks a lot about memory and context, and the reasons he's calling it Ralph is that it doesn't need to be smart. It just needs to keep trying.
Okay.
Yeah. But I think, so this is okay. Definitely check that.
Yeah, this is another repo that got famous. This is the ponytail. Yeah, so this is ponytail. It's like comic book guy and Ralph Wiggum, basically. He says nothing. He writes one line. It works. And
he should be able to replace you with a short
small shell script. Yes. Yeah, that's it. And then so it's like one line of code or a very small thing that you would use to, or I don't.
It's just a plugin. No, I haven't used it much, but means I haven't tried it yet. But from what I could see or get to know about it, it's like normally when you tell an LLM to write some code, it gives you a whole pile of code together. So there's also some redundancy or some irrelevant chunks that are there in the code. So Ponytail basically reiterates through that and only writes the code that is just necessary. So shortening the output code.
Okay.
So
that's yeah. That's something again that you sometimes really want. It's like you get some working code and then you're like, okay, now make this like a quarter of the size. Make this much more efficient.
Yeah.
But then you have to stop it where it's like, but also keep it, readable or like, it's
Yeah, we talked about sustainable shell scripting at one time. You were talking about that actually, and is that a very similar concept or?
Well, it's the same. It's a similar, it's a similar tension that you have in coding, right? Where it's just like you want sufficiently complex, but not overly, right? You want you want to capture like all the particular failure modes, and you want to make sure you got all the edge cases, but you want to also keep it readable and keep the psychology readable, right? Like these are great tensions. Good. And then you potentially have the issue of you want to keep the code fast, so like how's that being dealt with, or
yeah. Actually, it allows me to transition to something I want to talk about here. So we did have this discussion about shell script sustainability, and this is an article on what is a shell script in Linux. And so this is where you're using scripts to automate repetitive tasks, and usually this is a term they use in Linux for this. So in Linux, you're using the command line a lot, and you're automating things. You can do this in Slack as well. You can create a Slack bot, or you can do other things in a similar way, or like with what we were just talking about with harnesses. So a shell script in Linux is the idea is to boost efficiency and productivity. It also allows us to streamline complex workflows and ensure consistent execution of commands. So this is a tutorial that I pulled up that just kind of goes over shell scripts. So a lot of times you'll use this in programming projects. You might also use this in open source communities as a way to automate tasks that a lot of people might have to do repetitively, or sort of rote tasks that need to be done, but you don't want to devote human resources to it. So we talk about the shell. Systems admin people can utilize the shell as a user interface to access the services provided by the operating system. So the shell not only interprets the commands entered by the administrator, but also executes them. And then, of course, you can use bash or sh or csh or ksh or zash as different types of shells. And so then you have these shell scripts, which allow for automation, efficiency, customization, portability, and development. And then it just kind of shows how you execute a shell script. And then, of course, there are these different concepts in shell script, which is where you have things like shebang, which is a way to, specify the path to the interpreter. And then we have comments. So the shell discards comments during execution. So you might make a comment in your shell script and it automatically disregards those. Then you have variables, so you can have different things that are accessible throughout the script, like names or other things. You have control structures, which then are like these if-else statements. And so this is very much like a very rudimentary programming language, but just for the command line. And so the idea of sustainability, though, comes from if you have a lot of shell scripts and you need to have best practices across your organization, how do you manage that? So this is an article on sustainable coding, best practices for shell scripting. And then the subtitle here is Discover Sustainable Coding Practices for Reusability in Shell Scripting, Enhancing Efficiency and Maintainability in Your Projects. So this is where they talk about the importance of maintaining efficient code and how that should be a prime imperative. As software projects grow, the demand for tools that facilitate easier updates and modifications continue to rise. Writing scripts that retain their usefulness over time is crucial. This not only saves valuable resources, but also fosters collaboration among developers. And so one of the things that, again, we talked about sustainable programming earlier. That's something we covered in the open source meeting. And so it is with shell scripts. So one key aspect of creating lasting scripts is the emphasis on modular design. Modular components allow for easier testing and implementation of changes. Furthermore, this approach leads to improved readability, making it simpler for others to understand the underlying logic. When developers prioritize creating small reusable functions, they inherently boost the efficiency of their work. And so we just need to anticipate future needs and manage our shell scripts appropriately. So, but it's also about maintaining practice within the organization. So if you can maintain the development of good, effective shell scripts and making sure that everyone knows where they are and how to write consistent have a consistent method for writing shell scripts, then that helps you out. So this is where we want to minimize technical debt and enable rapid adaptation to new requirements. But we can't do that if our method for creating shell scripts is such that there are no standards, and then we spend time having to debug those. And then, of course, adding proper documentation is essential, and not only aids future developers, but also enhances the usability of scripts. Maintaining clarity in code contributes to better maintenance and understanding. And then, being able to take modular scripts or these scripts that have some structure to them is a way to enhance efficiency. So breaking down complex tasks into smaller manageable units can significantly boost productivity. The approach not only simplifies maintenance, but also enhances the clarity of the overall process. Each component can be developed, tested, and debugged independently, which leads to a more streamlined workflow. As well, modular scripts allow for easier collaboration among team members, as individuals can work on different modules simultaneously without stepping on each other's toes. So a recent survey indicated that 70% of developers prefer modular approaches due to their flexibility and ease of understanding. So this, and then they illustrate this with a scenario where a script for file backup needs enhancement. Instead of rewriting the entire script, you can simply update the backup module. This way you retain the integrity of the original functionality while incorporating new features. Okay, so I think that's, kind of a nice discussion about thinking about these kinds of tools that we use for programming and how we manage them in our organizations. This is something, Morgan, but Yummy Melon. This is
Well, it's just I was thinking about how how I got started with shell script, and how how utterly life-changing it is. Yeah. And and it makes me think about again, it just being a bit of a student of the history of science and computer science and coding as well. That there was the what's it called, the Hacker Manifesto. Was it Eric Raymond?
Yeah, I think so.
Anyway,
yeah.
But, and yeah, so it looks like everything you're saying about shell scripts is like so important, and so like if you've come to computing from Windows or Mac OS, right? Like it can be or you've only used a mobile phone or an iPad, like a tablet or something, right? Where it's like even more kind of limiting. Like the wonderful lessons that are in shell script for how to write processes and the design constraints that they used to allow for all their tools to be interoperable, so that I mean, again, from a kind of like coding sustainability, there's just like so many wonderful lessons in Unix about how to do how to settle that tension in coding, right?
Yeah.
About like making tools readable, making tools single purpose, but making them always interoperable with a common interface, right? Like, and anyway, and then it just kind of got me thinking about the coding today.
agentic coding allowing this kind of like personalized code, right? Where you can almost generate code to do your task, as opposed to relying on other people's code, right?
Yeah.
And you know, some of what, you know, like so Emacs and you know, Eric Raymond's big thing in that particular manifesto was that like you need to study Lisp just because it's conceptually such a different kind of programming language.
Yeah.
But that it's just super interesting that it's also the basis of this editor that absolutely can be, you know, that is customized, you know, endlessly. So without getting into debates about Phi versus Emacs, but if we just look at it as kind of like this, an early conception of this, where it's just like you absolutely built your own interface, you know, because it's like you tailored it to your workflow, your tasks, your things like that, right?
Yeah.
Yeah. Anyway, it's like, so I've just been playing with using LLMs together with Doom Emacs, to see, you know, like, yeah, what kind of synergy you can find there.
Yeah. Yeah.
So,
It's a good topic. We should come
okay.
back to it. Yeah.
Yeah. So I've got another project called Autonomic, which is is like putting the Tau agent harness in Doom Emacs, and
Okay.
so it's somewhat, it's actually, it's supposed to be a strange loop.
Right.
Because you're actually, you know, it's like you're putting it in Emacs so that you can understand Tau, but you're then using Tau to help you with your Emacs configuration and like help you with your Emacs programming.
Yeah.
Yeah.
Yeah. Well, that's great. Thank you. All right, I'm going to finish up with an article here. This is actually, let's see. This is actually a Substack article. This is by Inomen. And so this is just kind of talking about substrate agnostic cognitive architecture. So I guess the name of the Substack is Underlore. And the subtitle here is Closing the Gap Between Brain Science and Deployable Cognitive Systems. So this is very much in this spirit of biologically inspired cognitive architectures, or BICA. And so this is a diagram here. It's kind of highly conceptual, but you have like this emotion core, sensory input module, motor control unit, damage detection, auditory module, language center, logic processor, visual processor. So all these different multi-sensory inputs, control inputs, and memory storage, going kind of into this network that converges upon emotion. So that's kind of the idea here. So this abstract here, decades of neuroscience has established that the brain is a collection of functionally distinct regions with identifiable inputs, outputs, and computational roles. And we go to the history of neuroscience, where people have been able to localize function and measure that, and then figure out how that relates to behavior, and then more sort of relevant to some of the things we want to do with maybe AI or modeling, is to understand how they compute information. And so there's a whole field of computational neuroscience that talks about that. Simultaneously, machine learning has produced high-quality implementations of many of those functions in isolation. So it's just an approximation, say, of some output behavior. Now, of course, the problem is that we don't necessarily approximate the architecture. And a lot of people would argue that, well, that's not so important because a lot of these kinds of behaviors are architecture agnostic. But, it's not necessarily always the case. It's just kind of a general statement to say I can produce, say, like an emotional state on a very small amount of hardware or on a very small substrate. So if you think back to the Bradenberg vehicles, Valentina Bradenberg basically argued that you see these things that look like emotions coming out of a very small connection, what is essentially a connection machine, between sensors and effectors. Now, of course, if that's the same type of emotions that we would experience in humans or other types of complex emotional outputs is, that's debatable. So this idea of substrate agnosticism is, it's debatable. But the point being is that you can generate these different behaviors on different types of hardware, different types of neural substrates, etc. So then this goes on to say, yet no research program has combined both observations into their logical conclusion, which is a working cognitive system assembled from best fit substrate per region, coordinated over a shared event bus with no requirement for biological fidelity. Okay, so I guess he's saying that you could combine the outputs of different AI systems into one cognitive architecture. Okay. Existing efforts fail in one of several ways. They're substrate committed, demanding biological tissue or homogeneous tensor compute, where they are architecturally faithful but fill every module with the same kind of model. A fourth failure mode is from scratch neurosymbolic approach, which correctly identifies the learning problem but solves it by rebuilding everything rather than composing what already exists. So composition is important, where you're putting together pieces and getting them to work together. So, the idea of composition is important in linguistics, but it's also important in development, and it's important in these kinds of complex systems where you're trying to put together different aspects of, say, like a behavior. So we saw in the figure at the top here where emotion contains all of these different units and they contribute to the core. This paper characterizes the gap, surveys what is known about each major functional region, proposes clean interface contracts between regions, and then outlines the minimum credible path to working proof of concept. The required work is an engineering problem, not a scientific one, and is tractable with a small team and seed scale funding. So they're trying to sell people on this idea more so than trying to answer scientific questions. But that's okay for what we're trying to do here. So the introduction talks about the modular organization of the brain, which is not a hypothesis. Lesion studies, split brain experiments, and decades of functional imaging have produced a detailed circuit diagram of which regions handle what. Visual processing, episodic encoding, motor sequencing, executive planning, reward learning, and routing are all separable. Damage to one region produces specific predictable deficits, so they're not all interacting all the time. There is this separability between them. They can exhibit crosstalk. They can be combined into some downstream thing, but they do have their own sort of substrate. You can produce different. You can propose different substrates to get the same behavior. You also have this localization of function, where if you damage one part of that substrate, you can impair this aspect of behavior. So the system is not homogeneous. Machine learning has, in parallel, produced strong implementations in many of these functions. Convolutional transformer architectures match or exceed human performance on visual recognition. Larger language models handle reasoning, planning, and language production at a level that was not expected this decade. Reinforcement learning systems learn reward-driven behavior. Vector databases provide fast associative retrieval. These are not approximations. For their target functions, they work. The logical synthesis is clear. Treat each brain region as a functional specification. Implement it with whatever substrate best fits its computational profile. Define clean interfaces between regions, and then wire them together. No one has done this. This paper asks why, characterizes the current gap in the literature, and proposes the minimum viable path forward. Okay, so then the second part is why existing approaches fall short, and it has to do with this substrate, which is what the computations run on. So in the brain, of course, our substrate is the neural architecture. So we might have a pathway with different neural centers, or we might have different neurons that do different things. In a computer, we have, maybe like a neural network or some sort of computational model that has different processing components. And the idea is that, you shouldn't need any one substrate to get the same behavior. So you can have, say, like a reinforcement learning model and a neural network, and they can give you similar outputs. The substrate being quite different, perhaps, but it gives you the same behavior. You can do computation on a number of things. And if we see this with organoids and neural cultures, where we can basically produce output behaviors for things like robots or other types of neural representations using sort of disembodied neural systems. So that's kind of the idea. So the first point here is substrate committed simulation. So he talks about the Human Brain Project and Blue Brain Project, and they pursue this biological fidelity as a primary goal. But then the problem is that you can produce a scientifically interesting output, but it doesn't provide a path to a working cognitive system on any near-term timescale. Fidelity and function are different targets. A perfect simulation of a wing does not fly. That's the criticism of this approach of mass neural simulation or emulation. The second point is substrate committed hardware. So neuromorphic machines or neuromorphic programs especially the ones committed to spike-based computation as a substrate principle, might be appropriate for some functions and entirely inappropriate for others. Spike-based computation is not a good substrate for large-scale language modeling, for example. Choosing a substrate first and then fitting the function to it inverts the correct design order. Then they talk about homogeneous machine learning architectures, where you implement every region with the same model type, typically a large language model or standard neural network. This abandons the efficiency and appropriateness gains that motivate the decomposition in the first place. So, for example, a cerebellum implemented as a 70 billion parameter language model is not a cerebellum. The cerebellum, in terms of the neural architecture, in terms of the neuroanatomy, is very specific to timing and movement and timing out things like that. And the architecture is very unsuited to a language model, or at least the language circuits that we have in biological brains. Then this fourth point, neurosymbolic from scratch approaches. So this just talks about the failure modes of neurosymbolic architectures. They correctly identify that frozen statistical models cannot perform real-time incremental learning, correctly reject the patch and LLM approach, and correctly center knowledge representation as the architectural backbone. The result is a system capable of one-shot learning, but then the failure mode is actually strategic, building every cognitive mechanism from scratch, including the knowledge graph, the learning engine, etc., into a single integrated system requires rebuilding what already exists at a considerable cost over a long timeline. The fifth point is the whole brain architecture exception, which is this whole brain architecture initiative. And this is something that is also what they're proposing in this paper. It separates the reference architecture from the component implementation and develops them independently. And then this is just talking about how this might work and how this might be an exception to all these problems. The gap is not scientific. We know what each region does. The gap is that no one has treated the system. This is a systems engineering project with the appropriate interface discipline. Okay, so then it goes on to talk about different functional specifications by region, the integration layer, the learning loop, tool use and agency, then the minimum viable path to this. So what are the steps that you need to implement? So step 1 is writing the interface specification. Step 2 is implementing the bus and prefrontal module. Step 3 is adding the hippocampal and thalamic modules. Step 4 is adding the sensory and basal ganglia module, so adding in these different components of the quote unquote brain, these homogeneous or heterogeneous components. And then step 5 is evaluation and publication of the proof of concept. Then this is just kind of, so it's kind of an outline of a thing that they want to do, but it also, I think, hits on a number of really good points about this kind of approach. So the conclusion is that a substrate agnostic interface for systems and engineering approach to cognitive architectures is tractable. The brain is a collection of parts, so we know what those parts do. We have good implementations of most of them, but getting them assembled into one heterogeneous system is the problem. Okay, any comments or questions?
Yeah, I mean, I like the it's at least trying to be thoughtful about the difficulty of us. It's really neuroscientists that are generating these models, and of course we've got a bias. I'm still I'm still not sure what we're trying. Well, it's like, what are we trying to abstract? But it's worth thinking about for sure. Like what is, I don't want to say embodiment free, but certainly embodiment agnostic.
Yeah.
I guess sort of going back to your point about like or talking about Hofstadter, there's still a lot of ways that embody,
Oh yeah.
The embodiment can or kind of in like an 11 way, there's many forms of cognition. Yeah. So who put that together?
This was this person here, Inamem, and I'm not sure who they are other than like just someone who were. There's no other ID here.
Okay.
Yeah. But yeah, this I guess they're looking for funding.
I mean, I definitely recognize some of the references.
Oh yeah. This is that area, the key references.
Yeah.
All right. Well, what do we call it a meeting? Thanks everyone, and talk to you next week.
Sounds good. Take
Thank
care.
you. Take care. Bye.